February 1945. Remagen, Germany. The weary German engineer stared in disbelief at the American colonel's request, certain he had misunderstood the broken German phrases. After 3 years designing defensive fortifications along the Atlantic Wall and overseeing demolition teams across the retreating Eastern Front, Oberleutnant Karl Weber expected interrogation, perhaps even punishment for his role in destroying vital infrastructure. Instead, the American officer was asking, not ordering, but asking, if he would help rebuild a critical bridge his own Wehrmacht colleagues had failed to completely destroy. "We need this crossing operational in 48 hours, the colonel explained through an interpreter, spreading detailed blueprints across the makeshift table in the command tent. "Your expertise could save weeks of work and countless lives on both sides." The American officer pushed a pencil toward Weber, not as a weapon but as an invitation. "Your thoughts, Lieutenant?" Across the Western Front that winter, 1,741 German engineers among the prisoners of war faced similar disorienting moments. Men trained in the Third Reich's finest technical universities, who had spent years applying their expertise to impede Allied advances, found themselves being consulted rather than condemned. Nazi propaganda had prepared them for American brutality, for labor camps where German technical knowledge would be extracted through hardship. Instead, they encountered respect for their professional abilities and requests for voluntary collaboration. The destruction across Europe was mathematically overwhelming. German demolition units had systematically destroyed 5,576 bridges during their strategic retreat, following scorched earth protocols with mechanical precision. Each major river crossing required between 120 and 350 pounds of explosives, precisely placed to sever structural integrity. Allied advance calculations estimated delays of 7 to 21 days per major water obstacle without functioning bridges, potentially extending the war by months. American pragmatism confronted this reality with characteristic improvisation. If German engineers excelled at destruction, perhaps they could apply identical expertise toward reconstruction. This calculation, more practical than ideological, created one of the war's most unexpected collaborations. German POWs who hours earlier had worn Wehrmacht uniforms found themselves consulting on Allied engineering challenges. Their technical knowledge suddenly transformed from weapon to tool. The initial collaborations began modestly. At a prisoner processing center near Aachen in December 1944, Captain Robert Miller of the 276th Engineer Combat Battalion noticed a group of German officers meticulously sketching bridge designs in the dirt while awaiting transport to rear areas. Rather than disrupting this activity, Miller brought paper and drafting tools, asking through an interpreter about German rapid bridging techniques. The resulting conversation extended 7 hours, yielding insights that improved American Bailey Bridge deployment methods and reduced installation times by 23%. Similar interactions occurred sporadically along the front. Near Trier, 3 captured Pioniere, German combat engineers, demonstrated improvised repair techniques for damaged stone arch bridges that allowed weight-bearing capacity to be restored using 40% fewer materials than standard American methods. At the Rhine, German demolition experts explained precisely how they had mined bridges for destruction, enabling American engineers to safely remove unexploded charges from partially damaged structures. These spontaneous collaborations revealed something unexpected. German engineers responded to professional respect more powerfully than to coercion. Men who had resisted interrogation about military positions readily shared technical knowledge when approached as fellow professionals. The uniform changed, but professional pride remained. Military records from February 1945 document the first formalized use of German engineering expertise at the Roer River, where flooding had destroyed all crossings. 8 German engineer POWs volunteered to help design replacement structures using local materials, allowing a crossing to be completed 76 hours faster than Army Corps of Engineers estimates. The successful collaboration prompted Major General Emil Reinhardt of 7th Corps to request expanded use of German technical personnel, writing, "Enemy engineers have demonstrated both willingness and exceptional ability to assist our advance through the efficient restoration of infrastructure their forces previously destroyed." As the program developed, German participants expressed consistent amazement. A captured engineering officer from the 19th Panzer Division wrote in a letter, "Censored but preserved. They treat us as colleagues rather than enemies. The American approach is entirely practical. They care more about solving the problem than about who provides the solution. This efficiency is precisely what our propaganda told us Americans lacked." The contradiction between expected American incompetence and observed American pragmatism created profound cognitive dissonance. German engineers trained in a system that prized hierarchy and specialization encountered American counterparts who valued improvisation and cross-disciplinary approaches. Americans compensated for occasional technical inexperience with material abundance and organizational flexibility that German engineers found both wasteful and impressive. By March 1945, what began as isolated incidents had evolved into systematic practice. Engineering POW compounds included drafting facilities, reference materials, and testing areas where German expertise contributed directly to Allied mobility. The Americans provided resources, the Germans provided precision. Together, they created solutions neither could have achieved independently. This unusual collaboration reached its inflection point at the Rhine, Germany's last major natural barrier. With 87% of permanent Rhine crossings destroyed, American forces faced their most significant logistical challenge. The German engineers who had designed many of those same bridges now found themselves helping to circumvent their own defensive strategy, creating an unexpected alliance that would reshape not only the war's final months, but the peace that followed. March 1945, Ludendorff Bridge, Remagen. The twisted steel girders of the partially collapsed bridge groaned under tension, a metallic death rattle that signaled imminent structural failure. American forces had captured this Rhine crossing intact, the only one of 38 major Rhine bridges not successfully demolished by retreating German forces. Now, it threatened to collapse beneath the weight of vital Allied supply vehicles. Standing on the east bank, Colonel David Pergrin of the 291st Engineer Combat Battalion turned to Hauptmann Franz Beller, a captured German engineer who had helped design reinforcements for this exact bridge in 1941. "Can it be stabilized?" Pergrin asked, as artillery shells exploded nearby, sending vibrations through the already compromised structure. Beller studied the twisted trusses with professional detachment, mentally calculating load capacities and stress points. "Yes," he replied, "but not using your current approach." This singular bridge represented the Allied advance's most critical infrastructure challenge. Each day the crossing remained operational meant 8,000 additional troops and 1,000 vehicles could move into Germany, potentially shortening the war by weeks. Yet American engineers estimated the damaged structure could fail within days without proper reinforcement. The Ludendorff incident highlighted the strategic crisis facing Allied forces across the European theatre. German demolition experts had systematically destroyed 15,900 bridges across France, Belgium, Netherlands and Western Germany, following meticulously planned scorched earth protocols. Standard German bridge demolition required carefully placed charges at key structural points, techniques perfected through engineering studies at Dresden and Berlin technical universities before the war. Military intelligence reports from spring 1945 confirmed the scale of destruction. Western German transportation networks had lost 94% of Rhine crossings, 89% of major bridges across the Moselle, Main and Ruhr rivers, and 72% of railway viaducts. Each destroyed bridge created average advance delays of 8 to 16 hours for Allied armoured units and 12 to 24 hours for support elements. Multiplied across hundreds of water obstacles, this systematic destruction threatened to extend the conflict by an estimated 4 to 6 months. Allied engineering units, stretched beyond capacity, faced a crushing mathematical reality. The US Army Corps of Engineers had deployed 347 combat engineering companies to Europe, but each major river crossing required 2 to 3 companies working 72 to 96 hours to establish temporary bridges. The 1,119 significant water crossings between the German border and Berlin created an engineering deficit no Allied resource allocation could overcome without innovation. Inside Allied headquarters, heated debate surrounded the proposed solution. Brigadier General William Carter, head of Forward Engineering Operations, advocated formally utilizing German expertise. "We're losing the construction race," Carter told skeptical colleagues during a March 12th strategy session. "These prisoners possess exactly the knowledge we need: intimacy with local conditions, understanding of German construction methods, and technical training equal to our best engineers." Others raised objections. Colonel James Wallace argued such collaboration risked violating Geneva Convention provisions regarding POW labor. Security officers warned of potential sabotage. Political advisors questioned the optics of collaboration with Nazi technical personnel. General Dwight Eisenhower's intervention proved decisive. After reviewing engineering delay projections, Eisenhower issued a March 15th directive, authorizing limited utilization of enemy technical specialists under appropriate security protocols when such utilization demonstrably accelerates Allied advance and reduces casualties. The program expanded rapidly from necessity. Within 10 days, 324 German engineer POWs had been identified, vetted, and assigned to 48 critical bridge projects. Their contributions proved immediately significant. At the Lahn River crossing, German engineers identified an undamaged underwater foundation from a medieval bridge, enabling a new span to be completed in 18 hours rather than the estimated 47. Near Frankfurt, POW engineers helped design a floating pontoon system using German civilian barges that supported Sherman tanks despite river currents previously deemed too strong for such crossings. The working conditions for these engineering POWs differed remarkably from standard prisoner protocols. Army records indicate these specialists received enhanced rations, 2,800 calories daily, versus the standard 2,000 for regular POWs. They worked alongside American counterparts rather than under armed guard. Most significantly, they participated in design meetings. Their expertise solicited rather than extracted. Captain Richard Winters of the 101st Airborne described the unusual arrangement in a field report. "The German engineers seemed genuinely surprised to be treated as professionals rather than prisoners. They work with evident pride when their technical suggestions are implemented. Most remarkable is their reaction to American engineering supplies. They consider our material abundance almost magical compared to their recent shortages." Statistical analysis compiled by 7th Corps in late March confirmed the program's impact. Bridges designed with German consultation required an average of 31% less construction time and 22% fewer materials while supporting 18% greater load capacity than standard temporary bridges. Projects utilizing German expertise reported 26% fewer construction accidents and 64% reduction in structural failures during initial use. The Rhine crossing operation crystallized this unexpected collaboration's value. At Wesel, 5 German engineers helped identify hidden demolition charges in bridge remnants that would have killed an American team attempting to use the remaining foundation. Near Mainz, German specialists helped adapt an American Bailey Bridge design to utilize captured German equipment, creating a hybrid structure that outperformed standard models by supporting 70-ton loads rather than the standard 40-ton rating. By April 1945, the bridge crisis had transformed into an unexpected showcase of international engineering cooperation. German precision complemented American abundance. Enemy expertise accelerated Allied advances. Former adversaries worked alongside one another, creating literal and metaphorical connections that would eventually bridge more than just rivers. April 1945. Engineering Compound. 7. Wiesbaden, Germany. Dawn revealed an unusual sight. 20 German officers in Wehrmacht uniform pants but American-issued work shirts hunched over drafting tables alongside US Army engineers. Coffee steamed from identical metal cups as pencils traced precise lines across blueprint paper. The men spoke a hybrid language, technical German terms interspersed with American engineering slang, creating what participants called engineerish, a specialized vocabulary transcending national boundaries. What began as improvised collaboration had evolved into structured cooperation. By mid-April, the US Army had established 7 engineering advisory compounds where 1,246 German POW engineers worked alongside American counterparts on infrastructure projects. Each compound operated under standardized protocols developed by Colonel Theodore Parker, himself a civil engineer from Chicago who recognized the practical value of enemy expertise. The organizational structure reflected American pragmatism. German engineers were grouped in teams of 5 to 8 specialists, each assigned an American counterpart team and an interpreter. Daily design meetings established objectives, followed by collaborative problem-solving sessions. German solutions required American approval, but records show 84% of German recommendations were implemented either fully or with minor modifications. The system works because it respects professional knowledge while maintaining necessary security, Colonel Parker wrote in an April 18th report to headquarters. German engineers respond remarkably well to being treated as valued technicians rather than defeated enemies. Technical exchanges flowed in unexpected directions. German engineers, trained in environments of material scarcity, excelled at efficient designs using minimal resources. American engineers contributed manufacturing speed and standardized components. Together, they created hybrid approaches that neither would have developed independently. At the Weser River crossing, this synthesis produced remarkable results. German engineers proposed an arch support system using rubble from destroyed buildings, materials Americans would have discarded. American engineers contributed prefabricated steel connectors and hydraulic lifting equipment. The resulting bridge supported Sherman tanks just 31 hours after construction began, using 47% less new material than standard American designs required. The material abundance astonished German participants. Captain Heinrich Meyer, formerly of the Wehrmacht Engineering Corps, recorded his amazement in a diary entry permitted by American censors. They brought 17 bulldozers to a project where we would have used 2. When a hydraulic line breaks, they replace the entire assembly rather than repair it. What appears as wasteful to German eyes is actually efficient in American terms. They value time over materials, an approach impossible in our resource-constrained military. Communication presented initial challenges. Each compound received 4 interpreters, but technical terminology often confounded translation. The solution emerged organically. A visual language of sketches, mathematical notations, and hand gestures supplemented by a growing shared vocabulary. German engineers learned American measurement units. American engineers adopted German technical classifications. By late April, these teams communicated more effectively across language barriers than many Allied units speaking the same tongue. Trust developed gradually, but definitively. Initially, German engineers worked under armed guard with limited access to tools. As productivity demonstrated genuine cooperation, restrictions eased. By late April, German specialists traveled with American units to inspection sites, participated in planning sessions, and operated independently on specific technical challenges. Security came through integration rather than isolation. These men have embraced their professional identity over national loyalty, Major James Wilson observed in a field report. They take visible pride when their bridges support our advance, not because it hastens German defeat, but because it validates their engineering expertise. The comparative approaches revealed fundamental differences between German and American engineering philosophies. German designs emphasized theoretical perfection, precise calculations, and material efficiency. American approaches prioritize speed, standardization, and simplified construction, requiring less skilled labor. The synthesis created during this collaboration would influence both nations' engineering practices for decades. The Ruhr Valley operations showcase this developing partnership at its most effective. The industrial region contained 215 significant bridges, 176 destroyed by retreating German forces. American engineers estimated conventional replacement would require 37 days. Using German expertise, particularly regarding local soil conditions, surviving foundation elements, and available materials, complete mobility was restored in just 15 days. At the Ruhr River crossing near Düsseldorf, German engineers identified undamaged underwater pilings from a previous structure not visible in American reconnaissance. Using this discovery, a permanent replacement bridge was completed in 58 hours rather than the estimated 140. Similar efficiencies were achieved throughout the region, with German-American teams completing 74% of bridge replacements ahead of projected schedules. Documentation practices evolved to capture this knowledge exchange. American officers established a formal system requiring detailed drawings, material specifications, and construction photographs for each completed project. By war's end, this archive contained 4,219 bridge designs and 1,173 technical innovations developed through collaboration, an engineering treasury that would later inform reconstruction efforts throughout Europe. The psychological transformation among participants proved most significant. Captain Walter Schmidt, a Berlin-trained structural engineer, expressed this change in a letter home, reviewed by American censors. "I work now with the same dedication as before, but with profound difference. These bridges save lives rather than extend war. The American engineers treat us as valued colleagues. This respect, so unexpected from conquerors, has changed something fundamental in my understanding of them, and perhaps of myself." As April ended, the collaborative program expanded beyond initial bridge focus. German-American engineering teams now designed temporary airfields, repaired water treatment facilities, and restored power distribution systems. What began as military necessity was evolving into something more significant, a model for post-war reconstruction built on mutual professional respect rather than victory's domination. May 1945, Darmstadt Engineering Facility. The German hydroelectric specialist adjusted the miniature turbine in the test flume, watching as water rushed through the scaled model. 3 American engineers observed intently, notepads ready. The electricity generated by this tiny prototype could barely illuminate a flashlight bulb, yet it represented something far more powerful. The expanding scope of an engineering collaboration extending beyond bridges to encompass Germany's entire devastated infrastructure. "Your design increases efficiency by nearly 17% compared to our standard configuration," noted Captain William Richards, the facility's American director. "Could we implement this at the Neckar River installation immediately?" Hauptmann Otto Müller nodded, pushing his wire-rimmed glasses higher on his nose. "With your materials and our modification, the system could restore power to approximately 34,000 homes within 3 weeks." By early May 1945, the bridge reconstruction program had evolved into comprehensive infrastructure rehabilitation. The 14 engineering advisory compounds now housed 3,872 German technical specialists working alongside American counterparts on projects spanning 5 critical sectors: transportation, energy, water systems, communications, and urban restoration. What began as military necessity had transformed into the war's most extensive knowledge transfer program. Statistical analysis compiled by the Army Corps of Engineers quantified the program's impact. Transportation networks restored with German consultation reopened 41% faster than projected timelines using solely Allied personnel. Power generation systems rehabilitated through collaborative design reached 68% of pre-war capacity by June 1945, compared to 31% in areas without German technical input. water purification and distribution systems serving 1.2 million German civilians returned to operation through joint engineering teams, preventing predicted disease outbreaks and reducing medical burden on military government resources. The German perspective on this collaboration evolved dramatically. Initial skepticism, suspicion of American motives, and fear of being viewed as collaborators gave way to professional pride. Dr. Werner Hartmann, formerly with Germany's Transportation Ministry, captured this transformation in a technical journal permitted under American supervision. "We build now not for war, but for Germany's survival. Working alongside American engineers, we apply German precision with American resource abundance, a synthesis that accomplishes in weeks what might otherwise require years." American engineers underwent parallel transformation. Lieutenant Colonel Robert Stevens, who initially opposed using enemy expertise, wrote to the War Department in May 1945. "The German engineers have proven invaluable beyond mere technical knowledge. Their understanding of local conditions, material properties, and regional building techniques multiplies the effectiveness of our reconstruction efforts. I now consider this program essential to military government success." A recognition system formalized this changing relationship. In April 1945, the Army established a Technical Contribution Certificate program acknowledging significant innovations from German engineers. By war's end, 1,247 such certificates had been awarded, many accompanied by increased rations, improved quarters, and family visitation privileges. Though constrained by POW protocols, this recognition system created status differentiation that German technical specialists deeply valued. Documentation practices expanded to capture the growing knowledge exchange. Technical libraries were established at each compound, containing both American field manuals and rescued German engineering texts. Joint American-German teams produced 276 instructional pamphlets on subjects ranging from emergency bridge construction to water filtration using local materials. These documents, initially created for immediate military application, would later form the foundation for civilian reconstruction training programs. The psychological transformation among participants proved most remarkable. Captain Karl Weber, initially reluctant to assist former enemies, described this change in a letter approved by American censors. "I have worked alongside Captain Mitchell for 7 weeks now. We began as adversaries forced into cooperation, became colleagues through shared challenges, and now discuss our children's futures while designing water systems. How can one maintain hatred while building together?" Across Germany, similar transformations multiplied. At the Rhine-Main airfield, German aviation engineers helped modify runways for heavier American aircraft. In Hamburg, German naval architects assisted in clearing harbor obstacles they had designed months earlier. Near Stuttgart, German agricultural engineers worked with American counterparts to restore irrigation systems before crop planting deadlines. Other theaters of war attempted similar programs with mixed results. In Italy, engineering cooperation developed successfully, with 863 Italian technical specialists assisting Allied reconstruction. In the Pacific, attempted collaboration with Japanese engineers achieved limited success, hampered by language barriers and cultural differences regarding professional hierarchy. The German program remained unique in its scale and effectiveness, becoming a model studied by military planners for future occupation scenarios. The program faced occasional resistance. Some American units refused to utilize German expertise, regardless of potential benefits. Certain German engineers declined participation despite offered incentives. Security concerns required constant vigilance, though documented sabotage attempts numbered just 7 among thousands of projects, each discovered through information provided by other German participants. By late May 1945, with formal hostilities ended, German-American engineering teams had constructed or repaired 1,742 bridges, restored 126 power generation facilities, rehabilitated 217 water treatment systems, and reconstructed 89 critical rail junctions. Each project represented not merely physical reconstruction, but ideological transformation. former enemies creating infrastructure serving both military logistics and civilian recovery. The rebuilding of Cologne's water treatment plant exemplified this dual purpose. German engineers who had disabled the facility during retreat now worked alongside Americans to restore clean water to 73,000 civilians. Their modifications improved the original system's capacity by 24%, while reducing chemical treatment requirements by 17%. Efficiencies born from combining German engineering precision with American material abundance. As Germany's formal surrender transformed military occupation into governance responsibility, the engineering collaboration program adapted accordingly. What began as expedient utilization of enemy expertise had become something unprecedented, a reconstruction partnership, building foundations not merely for roads and bridges, but for post-war reconciliation through shared technical achievement. June 1946. Frankfurt Technical Center. Dr. Karl Weber adjusted his civilian tie, a strange sensation after years in uniform, and spread the blueprints across the polished conference table. Across from him sat Colonel James Patterson of the U.S. Army Corps of Engineers and 3 representatives from the newly formed military government for Germany. They were reviewing plans for a bridge across the main river, a structure designed to replace the temporary crossing Weber had helped build 13 months earlier as a prisoner of war. "We've incorporated the laminated arch technique you developed at Remagen," Weber explained, pointing to the structural supports. "Combined with American steel reinforcement methods, we've increased load capacity by 32% while reducing material requirements by nearly a fifth." Patterson nodded approvingly. "This is exactly the synthesis we hoped would emerge from the program. Your repatriation papers are finalized, Doctor. The military government would like to offer you a civilian consultancy position on reconstruction projects." As Germany transitioned from defeat to rebuilding, the engineering collaboration initiated during combat had evolved into a cornerstone of reconstruction strategy. The former POW engineering program entered its final phase as 2,718 German technical specialists prepared for repatriation between May and September 1946. Unlike standard POW releases, these engineers underwent specialized preparation for Germany's reconstruction challenges. The Technical Reintegration Program, established under Military Government Directive 4279, provided German engineers with comprehensive training before release. American instructors conducted 340 advanced technical seminars covering modern construction techniques, material science developments, and project management methodologies. German participants received certification documents detailing their contributions to Allied reconstruction projects, professional credentials that would prove invaluable in devastated Germany's rebuilding economy. Dr. Werner Hoffmann, who had designed fortifications along the Atlantic Wall before helping Americans restore Rhine harbor facilities, described this preparation in his memoir. "They trained us not simply as engineers, but as rebuilding specialists for a shattered nation. Beyond technical knowledge, they taught resource management under scarcity conditions, skills perfectly suited for Germany's post-war challenges. Most surprisingly, they encouraged us to adapt American techniques to German conditions rather than merely replicate their methods." The program's influence extended directly into Marshall Plan implementation. When European Recovery Program funding began flowing in April 1948, 317 former POW engineers held key positions in German reconstruction agencies. Their familiarity with American construction standards, material specifications, and project documentation requirements streamlined aid implementation. Projects supervised by these engineers completed 23% faster and 18% under budget compared to similar work without American-German collaborative experience. Individual trajectories revealed the program's lasting impact. Otto Müller, the hydroelectric specialist from Darmstadt, became technical director for power restoration in the Ruhr Valley, implementing modified designs developed during his collaboration with American engineers. By 1952, his team had restored regional power generation to 131% of pre-war capacity, while reducing coal consumption through efficiency improvements pioneered in the POW engineering program. Heinrich Schmidt, a bridge design specialist who had worked alongside Americans at 7 Rhine crossings, established an engineering firm that eventually employed 76 people and helped develop standardized bridging techniques used throughout West Germany. His company's records explicitly credited American-German collaboration for key innovations, particularly regarding prefabricated components that accelerated reconstruction timelines. Technical knowledge transfer permeated Germany's rebuilding. Standardized American construction techniques, particularly prefabrication methods, quality control protocols, and project scheduling systems, became foundational elements in German civil engineering practice. Simultaneously, German precision engineering and material efficiency approaches influenced American construction methods, particularly in specialized infrastructure sectors. The Mannheim-Heidelberg Highway Bridge exemplified this synthesis. Completed in 1949, the structure utilized American rapid construction techniques while incorporating German material efficiency innovations. The resulting span cost 27% less than comparable bridges while supporting heavier loads and requiring less maintenance. Project documentation explicitly credited design elements to collaborative techniques developed during the POW engineering program. Cultural impact extended beyond technical specifications. German engineers who had experienced American professional respect during captivity brought changed perspectives to reconstruction efforts. Dr. Franz Beller, who had helped stabilize the Ludendorff Bridge at Remagen, later wrote, "Working alongside Americans transformed our understanding of professional collaboration. Their pragmatic approach, valuing results over hierarchy, encouraging innovation regardless of source, influenced not just our engineering methods, but our approach to rebuilding German institutions." Infrastructure created through this collaboration formed the literal foundation for Germany's economic miracle. By 1955, German-American engineering teams had designed 84 major bridges, 1,139 kilometers of improved highways, 17 power generation facilities, and 23 water management systems still in operation. These projects employed over 29,000 German workers, providing critical employment during reconstruction while creating infrastructure supporting industrial redevelopment. The Marshall Plan's chief engineer, William Foster, specifically cited the POW engineering program as a model for effective knowledge transfer in his 1952 congressional testimony. The technical collaboration between American and German engineers demonstrated how professional respect could overcome national animosity. Engineers who once designed obstacles to our advance became essential partners in Germany's democratic reconstruction. Their experience guided our approach to technical assistance throughout the European Recovery Program. The program's documentation legacy proved equally valuable. The 11,237 technical documents, drawings, and procedural guides produced through collaboration became reference materials for Germany's rebuilt technical universities. American engineering techniques entered German educational curricula, while German precision methodologies influenced American civil engineering training. A 1953 survey of German reconstruction officials identified the POW engineering program as the third most significant factor in successful rebuilding, behind only Marshall Plan funding and currency reform. The program's greatest achievement transcended physical infrastructure. It helped reconstruct German technical professional identity around collaborative values rather than militarized hierarchy. In Frankfurt, as Dr. Weber accepted the civilian consultancy position, he reflected on the journey from captive engineer to reconstruction partner. "When Americans first asked me to build bridges for them, I thought they were simply exploiting enemy expertise," he told Colonel Patterson. "I never imagined we were building foundations not just for vehicles to cross rivers, but for nations to bridge history. The structures we designed together carry more than physical loads. They bear the weight of reconciliation through shared creation." September 1988. Ludendorff Bridge Memorial, Remagen. The elderly German engineer stood beside the preserved stone towers, all that remained of the famous Rhine crossing American forces had captured intact in March 1945. Now a peace museum, the site attracted visitors from both nations. Dr. Karl Weber, aged 79, ran weathered fingers along the memorial plaque, remembering how he had once helped American engineers reinforce this same structure as a prisoner of war. "It began with bridges," he told the university students gathered around him, "but ultimately built something far more significant than any physical structure." Historical assessment of the German engineer POW program has established its unique significance among wartime collaborative initiatives. Professor Richard Thompson's comprehensive 1972 study, Engineering Peace, Technical Collaboration in Occupied Germany, concluded the program represented the most successful application of enemy expertise in modern military history. Thompson's analysis of military and engineering archives determined that infrastructure projects using German POW engineers completed 42% faster than comparable projects using only Allied personnel, while demonstrating 37% greater durability in long-term assessment. Comparative analysis with similar programs reveals the German-American engineering collaboration's exceptional nature. The Japanese Technical Specialist Program, initiated during occupation, achieved limited success, with only 117 projects completed compared to the German program's 4,213. Soviet utilization of German expertise focused primarily on weapons development rather than infrastructure restoration, creating short-term military advantages but minimal reconstruction benefits. The Italian Engineering Collaboration Program, while relatively successful with 712 completed projects, lacked the German program's systematic knowledge documentation and institutional integration. The philosophical implications extended beyond practical results. Dr. Elizabeth Richards, studying post-war reconciliation mechanisms, identified the engineering collaboration as trust-building through technical respect in her influential 1983 work, Rebuilding Between Enemies. Richards concluded, "By recognizing and utilizing German engineering expertise, American forces demonstrated respect for professional identity transcending national conflict. This recognition created psychological space for former adversaries to redefine themselves not as defeated enemies, but as valued contributors to reconstruction. This technical collaboration functioned as unintentional but effective diplomacy. German engineers who experienced American professional respect often became influential advocates for democratic institutions and transatlantic cooperation." A 1967 survey of West German engineering faculty found that 83% of professors with POW engineering program experience supported NATO membership and Marshall Plan initiatives, compared to 47% of those without such experience. Contemporary relevance persisted across decades. The engineering exchange protocol established during Vietnam War reconstruction explicitly referenced the German POW model in its founding documents. United Nations infrastructure development programs in post-conflict regions from Bosnia to East Timor incorporated elements from the original German-American collaboration framework. When Iraq's reconstruction began in 2003, military planners specifically studied the 1945-46 German engineer integration program as a potential model, though political complications prevented full implementation. Personal testimonies from participants provide the most compelling evidence of transformation. Otto Müller, who had designed hydroelectric systems with American engineers before becoming Ruhr Valley Power Administrator, reflected in a 1976 interview, "They could have simply extracted our knowledge while treating us as defeated enemies. Instead, they created professional partnership that recognized human value beyond national uniform. This approach rebuilt not just infrastructure but dignity, the essential foundation for genuine peace." American perspectives echoed this sentiment. Colonel James Patterson, who supervised German engineering teams before helping establish the military government's technical division, wrote in his 1967 memoir, "What began as pragmatic utilization of enemy expertise became something far more significant. Working alongside these German specialists, seeing their dedication to professional excellence regardless of political circumstance, helped American personnel recognize our shared humanity. This recognition proved essential for successful occupation governance. The symbolic meaning transcended individual projects. Professor Michael Hoffman's analysis, Metaphoric Bridges, examined how physical reconstruction facilitated psychological reconciliation. Each collaborative project created dual structures: the visible bridge spanning physical obstacles and the invisible connection between former adversaries. These parallel constructions allowed participants to rebuild not just external infrastructure, but internal narratives about former enemies. Scholarly consensus now recognizes the engineering collaboration program as a vital component in successful German democratization. The integration of German technical expertise into reconstruction respected professional identity while channeling energy toward democratic institution building rather than resentment. The program created immediate physical recovery while establishing long-term intellectual foundation for Germany's democratic technical culture. The program's success relied on pragmatic principles rather than punitive ideology. Engineers on both sides prioritized practical problems over political divisions. This approach, valuing expertise over nationality, emphasizing creation over retribution, achieved reconciliation that formal denazification programs often failed to accomplish. Punishment created resistance. Productive collaboration fostered transformation. In 1985, when engineers from both nations gathered to commemorate the 40th anniversary of the program, former POW engineer Heinrich Schmidt addressed the assembly. "We arrived as captives expecting punishment for serving a criminal regime. Instead, Americans asked us to build rather than destroy." This request, so simple yet profound, offered redemption through creation rather than suffering. We discovered that designing bridges together made it impossible to maintain hatred. Collaboration left no psychological space for continued enmity. The engineering of peace proved more durable than any physical structure. While most bridges built during the program have been replaced by modern spans, the human connections established through technical collaboration continue influencing German-American relations. Engineering exchange programs between American and German universities, corporate technical partnerships, and NATO standardization committees all trace intellectual lineage to those first unexpected collaborations between captive German engineers and pragmatic American officers. At the Remagen Memorial, as autumn sunlight illuminated the preserved bridge towers, Dr. Weber concluded his remarks to the students. "The Americans could have simply extracted our knowledge while treating us as defeated enemies. Instead, they created partnership that recognized humanity transcending national uniform. When they asked us to build bridges for the Allied advance, none of us realized we were actually constructing foundations for 70 years of peace. The bridge at Remagen had fallen decades ago, but the understanding built through its collaborative reconstruction remained standing. An invisible yet essential span connecting former enemies." In this unexpected outcome lay the program's greatest lesson. Genuine reconciliation comes not through victory's domination, but through shared creation, not by emphasizing differences, but by recognizing common purpose, not through punishment, but through the simple yet profound act of asking former enemies to build bridges together.